All right. If you can't see my notes for some reason, if they're too dark, let me know. I think it should be fine, but everything moved around in here again today. I had some very exciting things happen. I was bugging my husband for months because I wanted a Peloton treadmill, and it finally came today. He got tired of listening to me complain, so I had to move some things around. And my lamp ended up moving, so I don't have the lamp any longer that I can pull in. Luckily, the semester will be over soon, but let's see how it goes without my lamp. I moved it, so maybe it'll work better. I might just have to get the emulator. Okay, as far as your quiz is concerned, let me look at it. Wrong button. Okay. Did anyone want to see number 1, simplifying factorials, or do we feel okay about that? The few, the proud, the 7.
No, that question took me a little bit. I'm like, is it before or after?
Okay.
But I figured it out.
Okay. I'll just go over the whole thing though, just in case someone's not speaking up and they are stuck.
I kind of ran into problems with at the first derivative test. I knew I had to do it, well, and other stuff, but I ended up getting it right because I got the diverges that I did the series thing with the 1 over k, and that diverges, so I got converges conditionally. But yeah, we can go over that.
Okay. Let's see. So number 1, I'm gonna have to move this. There we go. Is just simplifying factorials, which you may or may not have learned in algebra. I don't remember ever covering this in algebra. I had to learn it in calc. Such is life. Okay, but I did do something like this with you when I went over the asynchronous lecture for 9-6. So you'll see I think I did 2 or 3 of these when I went through the 9-6 lecture. All right, so for the factorials, if you're thinking about going up to 3k, you might want to do the denominator first, and then take this up to 3k, and then 3k plus 1. And then in the numerator, you can leave this as 3k minus 2, 3k minus 1, 3k, and 3k plus 1. So just adding 1 to each successive factor that you put into this expression. And then you'll see that everything is going to cancel out up to a certain point. Now, in the denominator, oh, why did I go all the way up to, sorry. I'm very distracted because I should have put on my headphones. This is very distracting. Ever since daylight savings, my daughter wakes up from her nap just like irate, and she doesn't get over it for like a solid hour. Lots of Curious George involved, and that's all I hear right now. Okay, 3k minus 2. So in the denominator, that's what I should have included before the 3k. So I should have put it there, but that's okay. 3k minus 2, 3k minus 1 had to get put in before the 3k. Wait. All right, you guys, I'm losing it. I'm looking at the, all right, 3k minus 2. No, wait, I'm not losing it. Everything's fine. I'm going up to 3k plus 1. I had to start. I didn't have to start, but it's technically included that if I'm getting all the way up to the plus 1, I had to start at minus 2, minus 1, plus 0, plus 1, so on and so forth. And then up here in the numerator, I'm just going up to 3k minus 2, and that's the highest it's going to go. I can't go up to 3k minus 1 because that would be one more term. So I am going to go ahead then and cancel out anything that I can, which for me is, since I put these in the wrong order, I know it's going to go all the way up to 3k minus 2. However, that still leaves me with a 3k minus 1, a 3k, and a 3k plus 1. And if you find this confusing, It'll just take me like 2 seconds to rewrite this, so I might as well just rewrite it since I wrote it backwards. All right, so you have to hit 3k minus 2 first, then 3k minus 1, then 3k, then 3k plus 1. So when you start canceling, everything cancels up to 3k minus 2. And all you have left over at that point is what's left over in the denominator, which is 3k minus 1, 3k, and 3k plus 1. And these all shuffled, but I did one where you saw this expression in the denominator, then I did one where it was flipped, and I did one where I took a factor off, so on and so forth. Okay, questions on number 1? Okay. Number 2, determine the convergence or divergence. This went from k equals 1 to infinity. It's an alternating series, -1 to the k plus 1. And then you have k squared plus 2 divided by k cubed. So for this one, you have some options. One is that it converges conditionally. Converges absolutely is another one. You could say it diverges, or I put in like a cannot be determined. Of course, we can determine it. That was just my way of trying to throw you. It's an alternating series. And remember, if we're trying to look for whether the alternating series converges or diverges, we need to meet 2 conditions. One of them is that the limit as n approaches infinity of a sub n is 0. Check. You can show this. I mean, you don't have to really show much here. You know the numerator is growing more rapidly than the denominator. You can just use that fact. If you'd like, you can use L'Hopital's rule, or you can use the rule from algebra that states if the degree in the denominator is greater than the degree in the numerator, then the limit as n approaches infinity is 0. I guess when you learned it in algebra, it wasn't really a limit, but it was talking about horizontal asymptotes and end behavior. So we have that to be true. The other thing you would have to show would be that a sub n plus 1 is less than or equal to a sub n. This one, Greg, is this the one that you were talking about using the first derivative test with?
Yeah, there's whatchamacallit on both sides, on the top and the bottom. And I got the derivative, and then I was like, looked at my notes, and I forgot kind of what I did with it.
Okay.
Yeah.
Now, I will go through this using the first derivative test. Because this was a quiz that was unproctored, I kind of just assumed that you guys would be like, okay, well, the numerator is growing more rapidly. We're just going to take this for granted that this must be the case, because you didn't have to actually show anything because it was an unproctored quiz and I'm not looking at your work. However, we will look at this function. And I did state in the video guides, or not the video guide, in the asynchronous lecture, which I'm really glad that everybody watched because I had a couple people refer back to this particular one, that when you're looking at this on your test, if you have something other than a constant in the numerator on both sides, so if you have a variable expression in the numerator and the denominator, you need to use the first derivative test to show me that your function's non-increasing. So you're going to take your function and make it equal to x squared plus 2 divided by x cubed, and then you're just going to show that your function is decreasing for at least some index n, or k in our case. So when you take the first derivative, you're going to use the quotient rule. F prime g minus f g prime all divided by g squared. And you'll get 2x to the 4th minus 3x to the 4th minus 6x squared divided by x to the 6th. Let's see, minus 3x to the 4th minus 6x squared. Okay. And remember that for a rational expression, if we want it to be equal to 0, we're just wanting the numerator to be equal to 0. So I'm going to go ahead and take out the numerator separately. The denominator will be 0, where the derivative does not exist when x is equal to 0. We don't even need to worry about that because that's not part of our range here from 1 to infinity. So we're just going to focus on where the numerator is equal to 0. So that will be negative x to the fourth minus 6x squared is equal to 0. You have 2 minus 3, that's where the negative 1 comes from. If I were you, I would solve this by factoring. So you can take out a negative x squared, and that will leave you with x squared plus 6 equals 0. And then you'll have negative x squared equals 0, or you'll have x squared equals negative 6. Now, in this case, x equals 0, again, is not really going to make a difference to us normally, but you're going to see why it actually sort of matters in this case. You end up in a situation here where you have an answer that's not a real number, so we can't have x squared being negative. What that means is the only critical number that's occurring is occurring at 0. Now, even though that's not actually in our range from 1 to infinity, when you're talking about this function, the only time that you're going to change the property from increasing to decreasing or vice versa would be at x equals 0. So the function has an asymptote at 0, and to the right of 0 and to the left of 0, you could possibly have that behavior change. But it's only going to change either to the right of 0 or to the left of 0. So what you need to do is just choose a test point to the right of 0, because those are the values that we're heading towards when we're approaching infinity, which is what we're doing here, just talking about what's happening to the behavior of our function as n gets really large. So pick any test point you want. If you want to pick 1, that's fine. I know you're thinking like, well, technically we're starting at 1. It doesn't matter, because whatever the behavior is at any point past x equals 0 is going to be the behavior at any test point past 0. You could even use 0.0001 if you want to. It doesn't matter. So if you feel like 1 is just an easy number to use, that's fine. If you feel more comfortable using 2, that's fine also. So if you like that, I'll just say test x equals 2. To do that, you're going to take f prime of 2. And here's your f prime. Remember the numerator we simplified to negative x to the fourth minus 6 times 2 squared. I know I should have used 1 just because it's a smaller number that I would have to deal with, but that's okay. And then you can divide by the denominator, which was 2 to the 6th. Boy, I have a calculator in here somewhere. Yikes. My 6-year-old was homesick from school Monday and Tuesday. My husband was working from home, and now my whole desk is all his stuff. Moving my stuff, and now I can't find anything. All right, negative 2 to the fourth minus 6 times 2 squared divided by 2 to the 6th. You're going to get a negative number. The number you get is negative 5/8. It does not matter what number you get, it just matters that it's negative. So this is negative 16 and then minus 24. It's going to be negative no matter what you do, divided by a positive. So you would say that your first derivative tested at some point to the right of your critical number yields a negative. So you would say that f of x is decreasing on the interval from 0 to infinity, because there aren't any other critical numbers. If you had another critical number to the right of 0, you would want to test the rightmost one. But in this case, you just have the 1. You're just going to look to what happens at the right of that critical number. Okay, so if you do get more than one critical number, focus on what happens to the right of your largest critical number. Now, that was a major segue, because what I'm really talking about here is whether or not this series converges, and then the type of convergence of the series if it does. What we just showed was that the terms of the series are non-increasing. In fact, we know that this function is going to be decreasing from 0 to infinity. So now we can say check, and we have the 2 conditions that are met to show that our alternating series converges. Before I continue with this, are there any questions here? So now that we know it converges, what we're focusing on is the convergence conditional or absolute? So we're going to focus on this part of the series and determine if we didn't have it alternate, if we just had k squared plus 2 divided by k cubed, would that series converge or diverge? So we can write that series down. It was k squared plus 2 divided by k cubed. And then you're trying to determine, does this converge or diverge? Now, since we know the alternating series converges, if this one converges, then our convergence is going to be absolute. But if this one diverges, then our convergence will be conditional. Now, you should have some sort of an idea heading into this, what you expect to happen. But if I were you, I'd probably go with a comparison that usually works out really well anytime you have polynomial terms in your series. So I would say that this is approximately equal to k squared over k cubed. Lop off any terms that are not the lead term in your polynomial. And then this is 1 over k. Now 1 over k diverges. So we're expecting that this series is going to diverge, but we're going to have to show this by comparison. I'm going to do limit comparison because you know I love limit comparison. I can't help myself. I haven't done this in a few days, so very excited. I'm going to switch over to n here. So what I'm going to do is take the ratio. I'm going to take my series n squared plus 2 over n cubed, and I'm going to divide it by my comparison series, which will be 1 over n. So that will give me n squared plus 2 over n cubed. And then instead of dividing by 1 over n, I'll multiply by n. And your degrees are the same in the numerator and denominator. So the limit as n approaches infinity is going to be the ratio of the lead coefficients, which is going to be 1 over 1, which is 1. Therefore, your limit is 1. Here's where you have to remember now, you've learned a lot of tests and you need to remember what each test says. The limit comparison test, limit comparison, says that if you take the limit of the ratio of your test and your comparison test, if the limit is positive and finite, then both series either converge or diverge, depending on what your comparison series did. So since our harmonic series that we compare to diverges, we would say our limit is positive and finite, hence both series diverge. What this means, kind of bringing this back to what we originally had an alternating series. We said the alternating series converged. However, when we took out the alternating factor, when you take out -1 to the k plus 1, well, now you end up getting a series that diverges. What that means is that this series has to have the alternating piece to it if it's going to converge. When you take that away, it diverges. So your convergence is conditional on the fact that it alternates. So the alternating series, it still converges. We checked those two conditions and we found that they were met, but it converges conditionally because the comparison series or the limit comparison test with our harmonic series showed that both series are going to diverge. So if we ended up saying like, hey, we tested it against a convergent series and we got a positive finite value, then we would have gotten absolute convergence. But since this series diverges, our alternating series converges conditionally. Okay, and I hope that when you're looking at these, you're getting a really good sense of what's going to happen. So, I mean, I'm hoping you're getting to a point where you see this series and you already know what's going to happen. You're already in your mind kind of going to this point where you're saying, okay, this really is going to simplify down to something that looks like 1 over k, and just getting a really good idea of what you're expecting. Now, on your test, you can't just write like diverges or converges conditionally, you have to back that up with a test, and you have to state the test and show that the conditions of the test were met, the limit's positive and finite, yada, yada. But you should start to be getting a really good sense before you apply the test of what's actually happening with the series. That was number 2. Questions about number 2? Okay, so another one that I gave you that I specifically asked you to do limit comparison with was number 3. And this was 3 plus 2 square root k divided by k cubed. And I asked you to compare with the series 1 over k to the 5 halves. So 1 over k to the 5 halves is convergent because it's a p series and p is greater than 1. And because you can easily see that this is a convergent p series, I didn't want to just ask you, does it converge or diverge? I wanted to actually ask you what the limit was, because obviously if I'm asking you to compare with the convergent series, you're expecting it's going to converge. But you're going to apply the limit comparison test as stated in the directions to show that your series converges by showing that your limit is positive and finite. So there's your series. Here's the comparison. Instead of dividing by 1 over k to the 5 halves, multiply by k to the 5 halves. And then simplify. Now, when you multiply this out, you'll get 3 times k to the 5 halves plus twice. When you multiply with the same base, add the exponents. So this is k to the 1 half. When you add that to k to the 5 halves, you get k to the 6 halves, which is k cubed. And then in the denominator, you have k cubed. Now, remember, if you try to use L'Hopital's rule with these rational exponents, you'll end up in some sort of a mess. So your strategy is to divide by the highest power that you're seeing in the denominator. So you're going to divide every term by k cubed. And as long as you do this to every single term, then you're not actually changing the value of the expression. But what we are doing is getting some rational exponents into the denominator versus having them sit in the numerator. Because if you tried to take the limit here, you'd just get an indeterminate form where you had infinity over infinity. We'll rewrite this limit. And 5 halves minus 3 is negative half. So you're going to have 3 divided by k to the 1 half. If you want to switch that to the square root of k, that's also fine. Plus 2. And then in the denominator, you just have 1. Now, I'm writing this probably one more time than you would write it. But it's going to end up looking like this before you actually take the limit. Now, when you apply the limit and you send, look at this, I have n's and k's in the same expression, you guys. You know, I used to always only stick to one variable, and this never happened before. Try to get all swanky with it, and this happens. Okay, when you divide by infinity, your ratio goes to 0. So the limit is 2. The limit is finite and positive, hence both series are going to do the same thing. Your comparison series converged, so your series will also converge. So you would say converges, and the limit is 2. Okay. Once again, think about if you have a question on that one. I just realized why it was so loud in here. There was there's a baby monitor on. Questions on this one, number 3? Okay. The last one was number 4. I believe it was a root test question. Check. Okay. So we're going to use the root test to determine the convergence or divergence. We're going from 1 to infinity. The series is k over 4 to the kth power. Now remember that with the root test, what you're doing is you're taking the kth root, and then you're taking the limit as your function approaches, or as n approaches infinity. So you're taking the limit, I'll just send k off to infinity. I'm not going to switch it this time, of the kth root of k over 4 to the kth power. Now, the nice thing is that when you take the kth root, what you're really doing is you're dividing by k in the rational exponent. So that actually looks like this. Now the k over k will cancel, and you'll just be left with the limit as k approaches infinity of k over 4. And the limit there is equal to infinity. What's my question here? The limit is infinity. The series diverges. Yes. Yes, the limit is infinity. The series diverges is the answer for number 4. I gave you 2 diverge options and 2 converge options. Remember with the root test, we're talking about looking at the limit as you take the kth root, and then you're looking at the actual value of the limit. If the value of the limit is greater than 1, then your series diverges. If it's less than 1, it converges. If it's equal to 1, then your test is inconclusive. So that was number 4. I'm going to talk about power series. I think I'm only going to talk about power series tonight. If I have a few extra minutes, I might introduce parametric equations. We'll see. We will see. All right, your test is a week from today, November 17th, Test 3, and it's going to be 8-1 through 8-8. I will not have time to cover 8-9 and 8-10. I never do. Sometimes I don't even have time for 8-8, so we're doing okay. I really just don't want to end up cramming in chapter 9. So if you are really interested and you want to learn about the Maclaurin and Taylor polynomials in sections 9 and 10, feel free. I don't foresee you using it anytime in the immediate future. If you become a math major, you'll eventually kind of do a deep dive into them, but it's going to be way down the road, probably in grad school, if you decide to go that route in mathematics, which most of you probably won't. But I don't remember anyone saying that they wanted to be a math major, but I could be wrong. I didn't want to be a math major when I was in IDCC. That came later. Okay, so this is going to be your test next week, which is the 17th during our normal class time. So that is going to be the Wednesday before Thanksgiving. So next Wednesday after that, the 24th, we have no class because ECC is going on Thanksgiving break. If you have any on-campus classes, they stop at 5 p.m. Some teachers on the day of the break on that Wednesday, they don't even have class at all. So I think they're supposed to, but maybe they go a little light. But we don't have class, so you guys are kind of lucky that we're Monday, Wednesday. Well, I guess technically if we were Tuesday, Thursday, you wouldn't have class Thursday. But no class for Thanksgiving break. And then before you know it, it's going to be December, because 7 days from this day would have been the 31st, except November doesn't have 31 days. So by the time I see you after test 3, it's going to be December. And this will be wrapping this up. So my goal is tonight, I'm going to talk about 8-8 Power Series. I want to say that I think you'll enjoy it. If you enjoyed the ratio test, then you'll probably enjoy Power Series. It uses the ratio test. And I also like that 8-8 kind of pulls together a lot of concepts that you learned using the tests and the rest of the sections. Remember that 8-7 was like a synopsis. So if you're feeling like, wait a second, didn't she just cover 8-6? Now we're at 8-8. What happened? 8-7 is just a summary of tests. I put up some homework on it so that you could get some practice. I put it up last week, but it won't actually be due till the day of your test. So I had set the due date to the 17th so that you would have some time leading up to your test to practice. And if I write myself a sticky, I'll remember to assign you some review problems if there are many. Test 3 review, achieve. Okay, sticky up here. If not, though, I was kind of talking with some students as they were preparing for the last exam, and my suggestion was you might actually find it easier to prepare for your exam if you go through the chapter reviews in your book. The answers to the odd numbered questions, not only are they in the back of the book, which is also available in the e-text, but I uploaded to D2L the student solutions manuals for your textbook. Now, it only includes the odd numbered questions, but if you go under the content area on D2L, it's under Student Solutions Manual. You can look at the one, I mean, I have all of them up there, but you can look at the one from Chapter 8, and at the end of it will be the Chapter 8 review, and you can go through those problems and practice them, and then you can look at the Student Solutions Manual, which is more than just an answer, but it actually has it worked out so you can see what the method was and how they simplified things. You might actually find that to be more useful than Achieve as you're sort of putting everything together in preparation for your test next week. Now,
Yeah, I was going to say,
ahead,
I find those very helpful.
yeah, normally when I teach Calc 2, I have students always doing homework from the book, and then we have quizzes in class that I call homework quizzes, and it's like questions that are basically like from the homework, and whether you do well on the quiz basically depends on did you do your homework. So moving to online, I couldn't set things up that way because it would be very difficult to do in this type of format. So unfortunately with Achieve, we're sort of limited to what they have available, which isn't great. I didn't realize how bad it was going to be. It could be worse, but they had a lot more available with WebAssign, and then they switched us over to Achieve. Publisher did, not ECC. There was nothing we could do about it. But anyway, so tonight I'm going to talk about 8-8, which is Power Series. Technically, you have an asynchronous lecture that I'm going to be releasing to you by Friday morning. That is going to cover 9-1 and 9-2, maybe all of 9-2, maybe just part of it. You'll find that 9-1 is a pretty short section. It's basically just a lot of graphing parametric curves and parameterizing functions, just writing functions as parametric equations and vice versa. But as we move into chapter 9, you'll find that we're going to be talking mainly about two different types of ways to write functions. One way is using parameters, and another is to use polar coordinates. So we're going to be doing parametrics and polars. So if you've been looking in your calculator at the mode for all these years and it's always on function, you'll find that we are actually going to be using the parametric and polar modes starting next week. So 9-1's pretty straightforward. 9-2 is not too bad. 9-3 is going to be similar to 9-1. It's very a basic introduction to polar coordinates, and that will have to be the async. Why do I want to say that's week 13? I think so. So the async you're going to have after that, because you're going to have your quiz on the 17th, or your test on the 17th. So this is tonight. This is technically like what would have been Monday, but you can watch it at any point. Then you're going to have your test on Wednesday. Then you're going to have an async 9-3, 9-4. No class Thanksgiving. Gosh, I'm going to have to figure out how all this async stuff is going to work out over the break. But, and then I'll see you back on the 1st. And you technically have a test scheduled for test 4. 15 minus 7 is the 8th. Test 4 is going to be 12-8. So I'm going to see you the 1st, and then of course there'll be some asynchronous content, but you're going to have test 4 over chapter 9 on the 8th, and you're going to have your final on the 15th. I want to say it's the 15th. It might be the 14th, but I think it's the 15th.
So we're going to have that. We're going to have a lot of async and not a lot of time with you before our next test.
That's right. That's right. Yeah, the 15th it is. Yeah. So unfortunately, that's the way it's panning out. But of course, I'll still be on for office hours, so on and so forth, which have been meager in attendance as of late, which I guess not a bad thing. But yeah, that's just the way it is with Thanksgiving. So anyway, that's the plan. Chapter 9 has, I want to say, 6 sections to it. I can't remember, maybe we go through 5. Yeah, 6 sections. 9-5 and 9-6 are like going to be 1 section per day kind of sections. 9-5 is probably what I'll do here, and then 9-6 will just cover async week 15. 9-6. That's the way I think this is going to pan out. I'll have to look at that later. But yeah, you're right. Missing that class and having the test, it's just going to seem like everything's coming at you asynchronously. Right. But yes, that's the plan. If you have any questions about that, feel free to send me an email or ask me now or ask me after class. Whatever works for you. Okay, but here we go. Power series. I really like power series because I really like the ratio test probably. Let me get you a theorem here. 8 power series. Definition. If x is a variable, we're bringing x back into the mix. And a series, the form k goes from 0 to infinity, a sub k, x to the k, equals a sub naught plus the series from 1 to infinity of a sub k, x to the k, which is equal to a sub naught plus a sub 1x plus a sub 2x squared, so on and so forth, where the coefficients are constants. Is called a power series in X, or the power series centered at 0. It doesn't have to be centered at 0. I'll give you a second part of this definition, and that one moves the center of the power series over, but you're going to be working on them the same way. If you have a series from 0 to infinity of a sub k, and then this time instead of taking x to the k, you have x minus c to the k. This is called a power series centered at c. It's one of those things where you subtract it off and then that's the center. It's like the minus sign's built into the formula and the value that follows the minus sign is the center. So we're going to be using not only k's or n's, but we're also going to be using x's in our series today. Okay, and here's the theorem we're going to be working with. For a power series, exactly one of the following is true. So we're going to be looking at a situation here where we're going to have 3 cases. So we're either going to have this thing happening or that thing happening or the other thing happening. But exactly one of these things is going to happen with each series that we look at today. One thing that could happen is the series converges only if x equals c. Okay, so that is one of the things that you're going to see. We could have a series converges absolutely for all x. That's a possibility. What you're going to see most often, though, is that there's going to be some positive number r. For which the series converges absolutely. For all x, as long as the absolute value of x minus c is less than r. And diverges for all x such that the absolute value of x minus c is greater than r. Now, the behavior of the series where we're equal to r has to be determined separately. Okay, so I'm going to show you some examples where you're going to see these different things happen with your power series. And we'll talk about what happens when we actually have the situation where we're equal to R, which is what we're going to be doing when we're testing our endpoints of the series, which I will explain to you when we get there. So in class, I'd be looking around at all of you and seeing if you're still writing, if you're ready to go, but can't see anybody, so I don't know. I think you're done. All right, example number 1. So this is going to be the series, and we'll use n. We'll go from n equals 1 to infinity of n cubed times x plus 5 to the nth power divided by 6 to the nth power. All right, so what you're seeing here that's different than what you would normally see with the series, honestly, I think this is actually going to be easier to see at the end, but it's this x. So maybe not worrying about what's happening with this x, you might try to determine what was happening with this series, and you might even conclude that you would think that this series converged based on the fact that the denominator is growing pretty rapidly. It's an exponential expression versus a polynomial. Once, however, you start to include this variable factor where x can be any number, remember x is not bound by what's happening to n. N is the value that's increasing for 1 each term. X can be any value that we allow it to be. And of course, you would choose one for the series, in theory, if you were going to be working on that series. But X is the wild card here. So our goal is to really determine what's happening to the series based on what's happening with X. So we're going to come up with some values and say, okay, well, if X is between these values, maybe we would have convergence, or maybe we would have convergence no matter what X is, or maybe it doesn't matter what X is, the series is going to diverge anyway. That's really what we're going to be looking at here with these power series is, what if X is this, what if X is that, and just coming up with this radius of convergence for values that X could possibly take on that would allow the series to still converge. And the way that we're going to do this is by using the ratio test. Okay, so we're going to use the ratio test to determine the convergence. I'm going to skip right to the point where instead of dividing by a sub n plus 1 or dividing by a sub n, I'm just going to multiply by the reciprocal, just because I don't think you guys need to see the complex fraction. If you'd like, I can do it for the first one. I'll do it for the first one, and then after that, I'll just skip to multiplying by the reciprocal. So you're going to start out with the n plus 1th term. So and remember, this is the n plus 1th, not the x plus 1th. You're only going to be using n plus 1 wherever you see n. It's not any variable, it's just n. So I'm going to take n plus 1 cubed times x plus 5 to the n plus 1 divided by 6 to the n plus 1. And then that's going to get divided by n cubed times x plus 5 to the n divided by 6 to the n. One thing you have to make sure you do here is everywhere you see n, you're going to have to use n plus 1 when you're in the numerator here. A lot of times students will remember to do it here, but they won't remember to do it in the exponent on the x expression. So just remember, everywhere you see n, you're going to have to use n plus 1 as long as you're looking at taking a sub n plus 1 divided by a sub n. All right, so now I'm going to write this as the multiplication by the reciprocal. If you'd like to simplify a little bit on the way, you can. Now, there's not a whole lot you can simplify. And since this is the first one, maybe I'll just let it be for now instead of doing two things at once. Because sometimes, honestly, the simplifying here is what gets students. They can't simplify the expression. A lot of times that's the case. So I want to make sure I go through these steps very methodically so that you see how everything got canceled and what was left over. Are there any questions before I continue? I mean, if you have them, you know, ask, or if you feel more comfortable using the raise hand feature, that's fine too. Okay. Wonderful. So to simplify this, what we're going to do, similar to what we did when we used the ratio test, is we're going to split up this base. Anytime we see some sort of an expression in the base being taken to an exponent that's written as a sum, we're going to split that up. So we're going to use that rule that says that a to the m plus n equals a to the m times a to the n. We're going to use that repeatedly today. We're going to use another exponent rule too when we get to it all. Make sure to call it out, but we're going to use this quite a bit. So when I rewrite this, the n plus 1 cubed can stay right where it is, but the x plus 5 to the n plus 1, we're going to write as x plus 5 to the n times x plus 5 to the first. Our goal here is just to get a bunch of stuff to cancel. In the denominator, I'll have 6 to the n times 6. And I don't have anything to change over here on the right-hand side, or on the second factor, I should say. And like I said, if you have questions, feel free to chime in. There are only 7 of you, so don't be shy. Can you imagine if we had an in-person class with only 7? How awesome that would be. You guys would be like such chums. It'd be amazing. Okay, I'm going to start canceling some stuff out. For instance, I see 6 to the nth power. Let's get rid of that. I also see x plus 5 to the nth power. Get rid of that. Now, whatever you do, don't cancel out the n cubes because you don't actually have n cubed. And remember, you can't write this as n cubed plus 1 cubed. You cannot distribute the exponents to a sum. It doesn't work that way. But we can simplify what we have. Now, I'm going to also take out some stuff that doesn't matter to us, but I'm going to group together what I know I can take the limit for. So for instance, and I'm going to write all this as one fraction, gather up what's left. If you want to write the 1/6 out front, you can. If you want to just keep it inside the limit now, that's fine too. I'm going to take anything that I'm not going to be working on the limit for, and I'm going to separate it. And then anything else is going to go into one fraction together. So for instance, n plus 1 cubed divided by n cubed. If you want to leave it split for now, that's fine. I'm of course going to rewrite this again. I'm so intent on writing my limits that I didn't leave some space. Let me explain what I mean by that. I'm talking about the limit as n approaches infinity. Notice that in this first factor, the way that I've split it up, there's no n there. And I know that you guys are only used to thinking about constants and pulling constants out of a limit, or coefficients, or however you want to think about them. But remember, x is going to take on some numerical value. We're not sure what it is yet. We're not taking the limit as x approaches infinity. We're taking the limit as n approaches infinity. In your mind right now, x is a constant. Take this entire expression outside of the limit. Now, when you take the limit here, you're going to run into some trouble if you leave this the way it is now. I mean, you can still technically do it. You can even just write this as the binomial cube. That's a little bit more work. You'll find this is probably easier if you just use that exponent rule that states Let me write the rule for you. A cubed, or say a to the n over b to the n. I'm trying to generalize these rules for you guys. Is a over b to the nth power. We'll use that exponent rule here. So the limit inside this expression, well, the degrees in the numerator and denominator are the same. The ratio is going to be the, or I'm sorry, the limit's going to be the ratio of the lead coefficients, which is 1, and then to the third power. So your limit here is x plus 5 to the 6th power. All right, so the any questions on the limit so far? Okay. I want to remind you, by the way, because I want to finish this one off. We have a little bit more to go on this, but I want to bring you back to the definition for the power series. When you are looking at the power series, you should be thinking that to you, this looks very much like what you would expect to see with the geometric series. You're looking at some ratio to the kth power. What we're going to focus on is setting our ratio to be less than 1 in order to determine if there's convergence here. If the ratio is greater than 1 for a geometric series, you will find that the series will diverge. So when we find our limit, we're going to force this quantity to be less than 1. Now, when I do that, it must be the case that the absolute value of the quantity is less than 1. And we need this for convergence. So thinking back to what we originally had, what I need, isolating that piece, is for our limit, the absolute value of the limit to be less than 1. Because remember, with the geometric series, we just needed the absolute value of r to be less than 1. And that's the way this is going to work for all of these. We're going to be using the same procedure each time. In order to solve this, we're going to take this absolute value. I'm going to remind you of something you did in algebra that you probably haven't done in a long time. You went through this period in algebra where you solved linear inequalities, or absolute value inequalities, even with linear expressions. And what you did was you said that if the absolute value is less than 1, then it must mean that the expression itself had to be between -1 and 1. Remember, when you're talking about the absolute value, you're just talking about a distance on a number line. So you're saying that if this distance is within 1 of 0, well, you can go up to 1 or down to 1 in the other direction, down to -1. So when you did this back in algebra, you rewrote your absolute value by smashing your expression between the negative and the positive variations of this number on the right-hand side. So what we're going to do now is solve for the values that x could be in order for us to have convergence for the series. So I'm going to solve the inequality by multiplying by 6 on both sides. Or I guess I should say all 3 parts. And then we'll subtract 5 from all 3 parts. You'll get -11 is less than x, which is less than 1. So x is between -11 and 1. Now, this is going to be part of your answer, but this is not quite finished yet. What was I going to say? Sorry, there are lots of things we have left to do here, actually. Little things, lots of little things that we have to check. There was something I was just going to say about this part. Oh yeah, so I kind of wanted to bring this back to the original expression. So this is stating that if x is some value in between -11 and 1, then it must be the case that your series is going to converge. But if it's a value outside of that range, then your series will diverge. Now, the nice thing is you can actually test this out, and you'll see how this works when we test the endpoints. But what we're going to have to do here is determine what actually happens at -11 and what actually happens at 1. On your test, when I ask you to work on power series, I'm going to ask you to test the endpoints. And a lot of students don't do this. I don't know why. I don't know if they just get to the end and they're like, okay, I'm done, or if maybe the idea of testing the endpoints never clicked. If we know that x can be between -11 and 1 for convergence, we're trying to figure out, well, what actually happens at -11? What actually happens at 1? And we're going to try to increase our convergence a little bit by just maybe seeing if we can get convergence at the endpoint instead of just strictly between the endpoints. So when you test the endpoints, you pick which one you want to start out with first. But we're going to say, let's let x be equal to -11. And I actually really like doing this because I think that it really helps to solidify the concept and helps you to understand what's actually happening with the function just by testing the endpoints. Now, what I'm going to have to do here is I'm going to have to pull the function back up. So this is the one that I'm going to use, and I'm going to let x be -11, and we're going to simplify it and see what happens with the series that we end up getting. So this is going to go like the series that you have from 1 to infinity. The n cubed is not going to change, and we're letting x be -11. So we have x plus 5 to the nth power, and then divided by 6 to the nth power. This is the series that I gave you. The only difference is we swapped out x for -11. And then we'll simplify. And you will have to show me your work for this. No cutting corners. -11 plus 5 is -6. And then we're going to simplify this again. Now, one of the exponent rules that we're going to be using quite a bit here is a times b to the mth power is a to the m times b to the m. We can distribute the exponent as long as we have a product inside the parentheses. We can't do it with addition or subtraction, but we can do it with multiplication. Now, if you're like, okay, fine, we don't have multiplication, we actually do. We have -1, I'm going to rewrite this up here actually. -6 to the n is equal to -1 times 6 to the n. And these are the kinds of things that you're going to have to get used to doing in this section. When you simplify that, you get -1 to the n times 6 to the n. I'm just using this rule for exponents. So when I simplify this, I'm getting -1 to the n times 6 to the n divided by 6 to the n. And then I can just see what's left over. I can cancel out the 6 to the nth powers. And this leaves me with the series from 1 to infinity of n cubed times -1 to the nth power. If you like it in the other order because you're used to seeing alternating series written with the alternating factor first, that's fine, write it like that, if that helps you to see it more clearly. Now, testing of the endpoints, maybe you're thinking like, oh, this is one small little thing I have to do. I mean, technically, but you can see how there's actually quite a bit of work involved in getting here. Well, now you have to look at this function. This is an alternating series. We need to figure out if it converges or diverges. The first thing you do with an alternating series is you take the limit as n approaches infinity of a sub n, and you see if it's equal to 0. Well, in our case, it's not equal to 0. It's equal to infinity. So you would say that the series diverges for x equals -11. Now, that has no bearing on what we've done so far. All this is saying is that we can't include -11 in the convergence. Oh well, you have to check it anyway. Sometimes you'll be able to include your endpoints and sometimes you won't. But we're also going to have to test the endpoint at 1. Before I do that, I just did a lot of things. Does anyone have a question so far? So now we'll test the right endpoint and we'll let x be 1, and we'll see if we can include some convergence at that endpoint. Notice how much work I did here. So when I say test the endpoints, I feel like sometimes students are like, it's just such a small thing, I'm not going to do it. There are actually quite a few points built in for this, just because there is some work to do here. So I'm going to tell you to do it. I'm going to remind you to do it. It's part of what you're supposed to do. Make sure you're doing it. So we're going to go from 1 to infinity. I'm taking my series again from our problem statement, but I'm letting x be 1 this time. So we'll have n cubed times 6 to the nth power divided by 6 to the nth power. Now these 6 to the n's will cancel. And here you can use the divergence test. I mean, I feel like most of us are going to look at this and you're like, yeah, clearly this is going to diverge, but you have to show me why. The limit as n approaches infinity of n cubed is infinity. So this one diverges by the divergence test. The divergence test, I know it seems like it was so long ago. I talked about the divergence test in 8.3. We talked about 3 things that day. It was asynchronous. One was the divergence test, another was the integral test, and another was p-series. So all of that was in the same day, if I can jog your memory. A quick way to show that your series diverges is just to take the limit as n approaches infinity and show that it's not equal to 0. Okay, so once you test the endpoints, in this case, we found that both of them gave us series that diverged. You're going to see that, okay, the endpoints aren't going to work here. We're not going to change our answer. So this is our convergence range here. We're going to say that as long as x is between -11 and 1, your series converges. One more thing you could say, and I think you're going to be asked for it on the homework, so I want to make sure to point it out. The radius of convergence. Well, note that from -11 to 1, you're actually covering 12 units. The radius is half of that. The radius is 6, but you'll also see that here. So the radius of convergence is 6. So starting from the center, which would be -5, you're going 6 to the left to get to -11, and then 6 to the right to get to 1. So your radius of convergence is 6. Your interval of convergence is usually written in interval notation. Just want to make sure I cover everything that you might possibly see. Is going to go from -11 to 1, and because we have these strict inequalities, we're going to use parentheses to denote that. Make sure and see what your directions are going to ask you to do specifically.
Quick question.
Yes.
So for the radius of conversion, you're basically taking the absolute value, so 11 plus 1 is 12, and then taking half of it?
Yes, yes. Mm-hmm.
Okay.
Yes. Yeah, and that's just because we weren't centered at 0 in this case. We were centered at -5. Remember, it's x minus c, where c is the center. X minus -5 is x plus 5. So since you're centered at -5, right, you're going 6 each direction. If you were centered at 0, you would just use whatever that value was, which I'll show you another one of those also, so that you can see it. You'll just be asked to find the radius of convergence and the interval of convergence. On your test, I'll probably just specify to use interval notation. I mean, this is fine, really. This is just inequality notation. It's fine. Not too worried about it. I probably don't even specify, just because I don't want to have to take points off if you write this instead of this. I'll just be really thrilled that you found the interval of convergence, and I'll probably just be glad. All right, so let's do another one of these. I have 3 more examples of this for you. I want to show you some other cases. I want you to be able to recognize when other types of things occur. Oh, you know what? I was going to say one more thing about this, actually. We tested the endpoints. We did not actually test any values that were inside of this interval or outside of the interval. But since you've seen how this works when you test the endpoints, if you're really not sure about your interval of convergence, you can always test other values. So, you know, maybe say you could test x equals 0 and be like, well, I don't know. Am I really sure this is going to converge for x equals 0? You can look at what actually happens if x equals 0. Notice that if x equals 0, you end up with 0 plus 5 to the n, and you end up with 5 to the n over 6 to the n, and that's 5, 6 to the n. So with the 5, 6 to the n, now you're looking at this geometric series where your ratio is going to be less than 1. So that makes sense in this instance why that would be the case. And then if you think about values outside of your range, like for instance, like if you went outside of the interval of convergence and chose something like x equals 2, well, now you can see why 2 is not going to work for you. 2 plus 5 is 7. Then you would have 7, 6 to the nth power. And that would force your geometric series to diverge because your ratio would be greater than 1. And of course, the polynomial function is not changing your expression very rapidly, as are these exponential expressions. So really, your answer is based off of just verifying that you can force this ratio to be less than 1 and get it to converge like a geometric series. So hopefully that is helpful. Okay. Example 2. This is going to be the series from 0 to infinity of x to the 2n divided by n factorial. All right, so I stated previously that next time I use the ratio test, I'm not going to show the ratio, I'm just going to invert and multiply. So we're always going to be using the ratio test when we're looking at power series. We're going to take the limit as n approaches infinity of x to the 2, and then make sure you put parentheses around your n plus 1 divided by n plus 1 factorial. And then you're going to multiply that by, and then you'll multiply by the reciprocal of your nth term. So n factorial divided by x to the 2n. And then we're going to simplify this and see what we end up with. You know what? I was just thinking I forgot about one important piece here. When we were doing the ratio test before, I had you leave the absolute value bars off because I was seeing in that section that as long as you're taking out the alternating piece, you don't need them. Technically, we do need them here because X could take on a negative value. We're so used to, in this section, thinking about all the variable values representing positive integers. However, remember that X can represent any real number, which includes negative numbers. So it is going to be important that we put absolute value bars on these. Totally forgot to include them. So I'm going to pop them on over here so that it's correct in your notes everywhere I see them. I know I used to have students completely overuse them, and now here I've forgotten to include them. It didn't actually make a difference for us in this case, but it potentially could make a difference for you depending on your function. Now, once you pull this out here, this part can't be negative. You don't need to worry about it, but here they would be needed. And I mean, we popped them on there anyway, just because we had to show that, but just put them on there. All right, I just wanted to make sure that was correct in your notes. All right, let's go ahead and simplify here. If you'd like to do some work off the side before you keep rewriting your limit, that's fine. I might just do that. I'll have x to the 2n plus 2 divided by x to the 2n. I'm just going to group these things the way that I find it to be most helpful to group them so that they can be simplified. So I'm going to call this side work. And then I'm going to rewrite this one as x to the 2n times x squared. Now, hopefully you guys did a bunch of this when you were working on your ratio test, but if you need a refresher, in the numerator you're going up to n, in the denominator you're not only just going up to n, but to n plus 1. So here we use that exponent rule that says if you're multiplying with the same base, you add the exponents, and we're undoing that. And now you can cancel those. Once you've simplified, if you're doing this outside of the limit, you can put this back on. Now you have the absolute value of x squared. And then the other piece of this is just going to have n in it, and you don't need to worry about 1 over n plus 1 being negative. So you can just write that as 1 over n plus 1. And technically, with x squared, you don't have to worry about that being negative either. But now that I've made such a big deal about putting absolute value bars on your expression, I almost don't want to take them away. We'll hold on to them for a minute. I mean, it's not going to hurt anything. It's just redundancy. You can pull that out as a constant if you'd like. You don't have to. As you look at this limit as n approaches infinity, note that the actual value of the expression is going to head to 0. So what we do, and I'm going to remind you, looking at the other exercise that we did, is we want to verify that the portion that we end up with after we take the limit is less than 1. So we got our limit in the first example, and then we said, okay, well, we're going to force that to be less than 1. However, in this case, our limit is actually 0. And 0 is less than 1. It is true all the time. So in that case, you actually have sort of a nice result here, because if this is going to be true all the time, what that means is it doesn't matter what the value of x is. X can be any number you want, and this series is going to converge regardless. And considering that you have a factorial in the denominator, I feel like that should be pretty intuitive. The exponential expression in the numerator is always going to grow more slowly than the factorial. And I know we usually think about exponential expressions as growing really rapidly, very quickly. They get large, but in the denominator, that factorial is growing even faster than the exponential that's in the numerator. So it would make sense that it doesn't matter what your base is here. The exponential expression is always going to grow more slowly than the factorial. So for that case, you have this situation where we limit 0, 0 is always less than 1. So we would say that our expression or our series is going to converge regardless of the value of x. So that means our series converges regardless of the value of x. Now, if that's true, that means that your interval of convergence can take on any value between -infinity and infinity. And then, of course, your radius of convergence would be infinity, because half of infinity is infinity. Okay, so that was a special case. You'll see this happens some of the time. In example 3, I'm going to show you another special case. Before I do example 3, are there any questions on example 2? Example 3. Now this series is going to go from 1 to infinity of n factorial times x to the nth power. Now I'm hoping that just by looking at this, you're thinking like, ooh, I have an idea what's going to happen here. I mean, think about it. The n factorial is not in the denominator in this case, it's in the numerator. You don't have a value in the denominator. No matter what x is going to be, you've still got this n factorial that's really making the terms of your series get large very quickly. But we're going to have to show this, what's happening here. I'm not going to tell you what it is, but I'm trying to plant the seed so that you're getting some sort of idea about what you think is going to happen. We're going to have to show that maybe there's some value of x that will cause this to converge. Maybe there's not some value of x that will cause this to converge. Hopefully you're making some conclusions right now on your own. We're going to do this by using the ratio test. I'm going to take n plus 1 factorial divided by x to the n plus 1. I'm going to multiply, not divided by x to the n plus 1. Sorry, I'm so used to having quotients in my expression. Okay, this is going to be n plus 1 factorial times x to the n plus 1 divided by n factorial times x to the n. It's almost weird to write that, isn't it? All right, we just simplified this in reverse in the last example. I don't know, I feel like we've done this a lot, but that's okay. I'll write it one more time. N factorial is going to look like that, or I'm sorry, n plus 1 factorial. N factorial is going to look like this. and then times x to the n times x divided by x to the n. So we're splitting up this expression here using that exponent rule. All right, now when I cancel out the n factorials, I'm going to cancel out x to the n. What that's going to leave me with, if I want to pull this out now, is the absolute value of x times the limit of, all I have left now is n plus 1. And this is the absolute value of x times infinity. And what we need to do is force this to be less than 1. But we're not going to get that to be less than 1 because infinity is never going to be less than 1. Okay, so it does not matter what x is. X times infinity is infinity. Infinity cannot be less than 1. So if that's the case, then we're going to have to say that the interval of convergence is 0 and the radius of convergence is 0. So for the radius of convergence, it's not converging anywhere. It can't go anywhere to the left or right, so that's 0. For the interval of convergence, sorry, I said 0, but I meant to write empty set. If you remember your set notation from algebra, if you just want to write the empty set, what this means is there's nothing in the set. So there are no values in here that will cause this series to converge. And if x is 0, by the way, then you don't have a series. You're just 0, and then you have nothing. So your interval of convergence will be the empty set if you're thinking about this in terms of interval notation, and your radius of convergence is 0 just because there's nowhere to go. A radius implies that you have some space on the left and the right, which you don't in this case. Okay. I want to do one more that's more traditional. Before I do that, are there any questions on example 3, that other special case? So I showed you example 1, where we had an interval of convergence and a radius of convergence. For example 2, you saw a situation where no matter what x was, you're going to have convergence regardless. And then in example 3, you saw the opposite scenario, which is no matter what x is, there's no way you're going to get this series to converge. But let's do a little bit more practice with a series we can work with. So this will be from n equals 1 to infinity of x minus 2. So we're centering this here at 2 to the nth power divided by the square root of n. I mostly just like to keep giving you these radicals because I think it's good for you to work with these limits. Okay. So that's the series we're working with. We're going to start out by taking the limit as n approaches infinity of the absolute value of x minus 2 to the n plus 1 divided by the square root of n plus 1 times the square root of n divided by x minus 2 to the nth power. Let's split this up. So this is x minus 2 to the first times x minus 2 to the nth. And then if you'd like, since you know you're going to be taking the limit anyway, first of all, we can cut off the absolute values on only the x expressions. You might want to write this as one radical. I know we tend to split these up a lot, but remember we have that property that I believe we used on the first example that says that we can take the limit of the inside function and then apply the square root to the limit. You'll find that will be easier in this case. But go ahead and cancel. Whatever you do, don't cancel your ends here. You cannot cancel between terms. So we are going to have x minus 2 times the limit as n approaches infinity of the square root of n over n plus 1. And remember, the property that I'm using here is that we can rewrite this as the square root of the limit. Feel free to use that liberally. And that will save you some work. Otherwise, you could have done this by dividing by the highest power in the denominator, which would be dividing by n under the radical. It will still work. It's just up to you the way that you decide to do that. This limit here is going to be 1, and the limit as n approaches infinity of 1 is 1. The square root of 1 is 1. And we're going to force that to be less than 1. So we're working now on getting the interval of convergence. Any questions here? All right, so we're going to take x minus 2. It's less than 1. What this means is that we can sandwich it between -1 and +1 by writing this as a compound inequality. And then add 2 on all 3 sides, all 3 parts. Okay, now don't put a box around this yet. This is maybe your interval of convergence, but remember we have to check the endpoints. It's possible that maybe if x equals 1, you're going to get convergence, or maybe if x equals 3. But we're not going to know until we test the endpoints. So you're close, but we're not there yet. And I know it's such a small thing, and you might end up with this same exact answer in the end, but this is a process. So we're going to go back to our original series, and everywhere we see x, first of all, we're going to test x equals 1. We're going to try that first. So we're going to look at 1 minus 2 to the n divided by the square root of n. So this is going to be -1 to the n divided by the square root of n. If you want, you can write that as times 1 over the square root of n, and then you'll have this looking more like a traditional alternating series. But it is an alternating series, and the really nice thing is hopefully you've seen enough of these, and this one's basic enough that you're realizing like, oh my gosh, holy cow, this alternating series actually converges, which it does. To figure out if your alternating series converges, remember, you just need to show 2 things. One of them is that the limit of a sub n is 0, check. And the other is that your terms are non-increasing, check. So we would say that the alternating series converges. So we actually have convergence at x equals 1. Okay, so here's what I'm going to do. Since we've already shown this, we have convergence of x equals 1. I'm going to set this to be a non-strict inequality, and we're going to include that endpoint at 1. We're also going to show this in interval notation when we're done checking the endpoints. This is good. Questions here? All right, so we also have to check 3, which is the right endpoint. So we have 3 minus 2 to the nth power divided by the square root of n. So this is just going to be positive 1 to the nth power divided by the square root of n. It actually makes a big difference that this is positive 1 to the nth power, because 1 to some sort of finite power is always going to be 1 regardless. So you can even just rewrite that by omitting 1 to the nth, because it's going to be 1 no matter what. This is a divergent p-series. Where p is equal to a half. So we did not get endpoint convergence at x equals 3. We did get it at 1. This is going to be your answer. So your interval of convergence, when we write this in interval notation, remember that if you have a less than or equal to sign, that's where you use a bracket instead of a parenthesis. So the interval of convergence is going to have a bracket at 1 and an open parenthesis at the right endpoint 3. And your radius of convergence well, remember that you're centered here at 2. To get from 2 to 3, you add 1. To get from 2 to 1, you subtract 1. So your radius of convergence is going to be just 1. Or like Becky said, you can just add them and then just take the difference. Okay. All right. Questions there? Okay. I should have said subtract them and take the difference. Sorry, I said add. Divide.
Well, if you
take the difference and divide by 2.
yeah.
Yeah. Take the difference. I'm getting all my operations all mixed up. Yes. Take the difference and divide by 2. 3 minus 1 is 2 divided by 2 and you get 1. Yes. All right. All right. I have 12 minutes, which okay. I'm going to show you one more thing, which I think is super straightforward, which is why, even though I only have 12 minutes, I think we're going to be okay in talking about it. It is still having to do with power series. I'm not going to make you do the derivatives and integrals with the power series because I feel like those can be really mind-boggling with series. I don't know, it's just rough for students to do, but I do want you to write your rewrite your power series. There's a definition in your book, and it has to do with what we were talking about with the geometric series. You can rewrite your geometric series as 1 over 1 minus r to find the sum. We can say the same thing for a power series, so we can represent this using x to the n instead of r to the n. So remember, this is just what we did with the geometric series. And then for a geometric series, we said that we needed to force r to the absolute value of r to be less than 1 in order for it to converge. So here, if we're talking about x, we could say that this converges for x, the absolute value being less than 1. And as long as we had this to be true, then we could say that the series would be represented by 1 over 1 minus x, assuming that you're starting here at 0. Of course, we would have to adjust that. But we're going to write our particular expressions as series. So we're going to go in reverse. Instead of what we did in 8.2, where I gave you the series and you wrote out the sum. And the reason we're going to do that is because I'm going to give you expressions involving x. Example, oh gosh, you know what? I started numbering these instead of alphabetizing them. So this is actually example 5. I'm going to give you different directions here, though. I'm going to give you the direction that says, I want it to exactly match your homework. It's going to say, find a power series representation of f. So we're going to use a geometric series to represent the function as a power series centered at 0. That's more specifically what we're doing in this example. And then we'll determine the radius and interval of convergence. A lot of times when you see interval of convergence, because it's so much to write, it's abbreviated as IOC and ROC. Hopefully we've used the terminology enough that it's not like, oh my gosh, what the heck is that? But we're talking about the interval of convergence and the radius of convergence. All right, so I'm going to show you how to do this. It's pretty straightforward. I don't think you'll have a hard time with it. The first series that I'm going to show you, or the first function, I should say, I'll give it to you in function notation, which you haven't seen in a while. Sometimes it's like, oh, this is kind of a breather to see function notation again. It's just going to be 1 over 1 plus x. Pull that back up there. All right, so our goal is to get it into this form where we have 1 over 1 minus x so that we can rewrite this as a power series. So what you're going to do is get it into this form by changing this to subtraction. And you're going to do that by writing this as a minus a negative. So rewriting that plus as minus a negative, now you have subtraction. Now, if we know that 1 over 1 minus x can be represented by this power series where we have x to the nth power, what we're going to do is replace this x with negative x. Whatever's behind the minus sign is going to be taken to the nth power. So we can say that this is equal to the series from 0 to infinity. And instead of saying x to the n, we're going to say negative x to the n. And once you have that, now we're going to take that variable that you have and force it to be less than 1. So we're going to, instead of saying the absolute value of x is less than 1, you're technically saying the absolute value of negative x is less than 1, which is really the same thing. It's absolute value. So it's going to work the same way. The absolute value of negative x can also be rewritten as the absolute value of positive x. And this would represent your interval of convergence in interval notation. And then you would say that the radius of convergence is 1. So I'm going to do another one of these, maybe even 2 more, but that's all you're doing. So I know you were expecting this to be crazy. It's not. This is literally all you're doing, is just doing a little bit of manipulation to rewrite the series. This one is going to be 1 over 1 minus x cubed. What we were going for was 1 over 1 minus some quantity. So we can, you don't even have to really do much here except just to say that your quantity behind the minus sign is x cubed. I mean, I know this is the exact same thing. We haven't really done anything, but it kind of makes it clear that the value behind the minus sign is what's going in as your base. So now you can take your series from 0 to infinity, and instead of writing this as x to the nth power, you're going to write it as x cubed to the nth power. And if you'd like to be extra fancy, remember that when you take a power to a power, you multiply the exponents. You can just rewrite this as x to the n power. I think either one is probably fine. This is technically the simplified version of it. Does not matter to me. And then you're going to get your interval of convergence by taking this quantity that's being taken to the nth power, and I'm going to use this form for that. You're going to take its absolute value and force it to be less than 1, which means that you have x cubed being between -1 and +1. Now, to solve for x in your inequality, you're going to take the cube root in all 3 parts. And remember, you can take the cube root of a negative number. So you are going to get an interval of convergence from -1 to 1 and a radius of convergence 1. Either one of these is fine. We'll do one more. That's all I have time for. C is 1 divided by, oh, I forgot the f of x. 1 plus 9x squared. Remember, what you're going for here is a minus sign in the denominator. In order to create that, you're going to write minus a negative. Now, technically, you're in the form that you need. So you can say that we're going from n equals 0 to infinity of -9x squared to the nth power. There are a bunch of different ways that you could rewrite that. Honestly, it's fine the way it is. And then you're going to set up your work for your interval of convergence. So you're going to take this expression, your r value, if you want to think about it that way, force it to be less than 1. Now, it's negative. If you want to pop the negative off, that's fine. No matter what, you would just end up flipping the inequality around, because remember, when you divide all 3 parts of an inequality by a negative, you flip your inequalities. But if you just want to take the negative off because it's an absolute value, that's also fine. So what I mean by that is that this is the same thing as saying that. They're equivalent expressions. Divide each part of this compound inequality by 9 and take the square root on each part. Now, you're going to end up in a problem there because you can't actually take the square root of your negative value here. What we can do, however, is you can keep this. Let's do it this way. Because it is squared. we don't want to lose this. You can take the 9 out. And then we can say, do it this way, that your x squared inside your absolute value bars has to be less than 1/9. And then when you take the square root of both sides, anytime you take the square root of both sides, remember you have to apply a plus or minus. So if I take the square root of 1/9, then we apply the plus or minus, and we would say that this value has to be in between negative 1/3 and positive 1/3. Now, if this seems odd to you because of the square, you can always work it back and make sure that it does satisfy the inequality. So if you were to choose a value here that's between 0 and negative 1/3, verify that that still makes your absolute value inequality true, which it does. So anyway, this is the interval of convergence, and your radius of convergence would be 1/3. Okay, that's all I have for you tonight. I'm out of time. I'm going to post an asynchronous lecture covering 9.1 and 9.2. We're going to, in chapter 9, head back to taking derivatives and talking about tangent lines, but using parametric curves. And then you'll find that as we work our way through chapter 9, we'll be using a lot more of the calculus techniques that you learned previously to find things like arc length and area of curves and stuff, but using different types of expressions that are not necessarily functions. Right, that's all. And like I said, oh, your test will stop at 8. So the stuff I'm posting for you asynchronously won't be on your test. I'm not going to make it due until after your test. You would have, a week from Monday, but make sure you get on that quickly, because then the following Monday you're going to have more asynchronous work. So don't forget about it. That's what I have to say about that. But I'll post something for you at some point, hopefully by Friday morning. I know most of you won't get started on it right away. Some of you will. We're only down to 7. I feel like the ones left will actually get going on that pretty quickly. Email me if you have questions. I'll be on in the office hour until 8:30. So feel free to stick around if you want to do that as well. Otherwise, have a wonderful evening, and I'll see you guys for your test next week. Good night.